All right, ladies and gentlemen. So, recording has started. I wanted to go through one of the new kind of problem that we're going to introduce starting today and then continue with it on Friday. If you did the problem with the vine on the one sheet that had the 4 problems up at the top of the backside or whatever set it was, it is similar to what we're going to do today, so that will help you. So if you work through that, that might help us, figure this out. So let's go here and let's take a look at number 1. My picture doesn't look so hot, but you guys have the picture there. And it says that a ball is attached to a string rotated at constant rate in a vertical circle with a radius of 85 centimeters. It says the ball has a mass of 0.3 kilograms and it rotates with a tangential speed of 4.1 meters per second. Very similar to the demonstration that we did on the very first day where we did this. Okay? So it says, what is the force applied by the string at the top of the motion? So if we take a look here, force applied by a string. That's just a fancy name for what? Or we said a fancy name for that is what? Tension, right? So part A is asking us for a tension force. Things they told us. They told us that the radius of the circle is 85 centimeters, so we'll just convert that into meters right away. 0.850 meters. They told us that the ball has a mass of 0.300 kilograms. And then it said it rotates with a tangential speed of 4.15 meters per second. Because the ball is going in a circular path, go here. Okay. Let's say that's the circular path of the ball. I know it's an oval, but we're kind of going in and out of the board, whatever. Okay. Up at the top, that looks like a good idea. Sorry, buddy. So there's our ball. Okay. In order for it to continue moving in a circle when it's at the very, very top, what does it have to have? Well, more generally, if it's moving in a circular path, it's got to have what? What causes things to move in a circular path? Centripetal force, right? You only did like 6 problems in the last hour based on centripetal force. But here's the middle of the path, right? So that means that at the top of the motion, there has to be a force on this ball that points which way? Downward. So it's going to look something like this. And we know that that force, right, has to be equal to mv squared over r. Now, one of the things we've done over the past couple of days is looked at there are different places that centripetal force can come from, right? Something has to provide centripetal force. So if we start looking at the forces that are acting on this ball, what's providing the centripetal force in this case? Well, there's definitely string force, right? Okay. And that string force is a tension force. Okay. Ooh, looks like that. However, is that the only force that's acting on the ball when it's at the top of its motion? Okay. We can't get rid of gravity. When the ball is at the very, very top of the motion, which way does gravity point? Downward. But more specifically, in the context of our problem, if a force is pointing downward when that ball is at the top of the motion, where is that force pointing towards? The center of rotation, which means, Lori, what is it helping us out with? What do we call forces that point towards the center of rotation? Centripetal force, right? So in this case, gravity is actually pointing towards the middle of our circle and helping us out. So does the string have to pull as hard at the top of the motion in order to provide the required centripetal force for that object to go around a circle? Because it's got help. Gravity's helping it out. It doesn't matter where this force comes from. All that matters is that we have this amount of force. Okay? So now, whereas in the past problems have started with f of c equals something, in this case, f of c is actually coming from a combination of two sources, right? What are the two things that are combining to give us the centripetal force? Gravity. And what else did we say was acting on that object? The string. So the combination of gravity and the tension force together provides us with the centripetal force. Okay? Does that make sense? What do we plug in for f of c? Okay, this goes mv squared over r. I hope by now we know how to calculate force gravity, right? That's just equal to what? M times g. And then what did we say we were ultimately trying to look for in this problem? The tension force. Do we know the mass of the object? We do. Do we know its tangential velocity? We do. Do we know the radius of that object, or the radius of the turn? We do. Do we know g? I hope so. Okay. So we go through now and solve for the tension force. Good. Is it 3.4? Sounds right if I remember correctly. Make it a second. Alright, is that good there? Any problems with where that came from? Okay. Let's take a look next at B. All right. Let me grab this. Oop. Grab this. And okay. In this case, we are still looking at too big. There's still our circular motion. But in the case of B, B says what is the force applied by the string at the bottom of the motion. So now our object is down here. Forces that are acting on our object in that point, at that point right there. Okay. Now we have gravity. Gravity's still acting which way? Down. So we got this gravitational force. What else is acting on that object? The tension is, well, the combination has to do that, but specifically, what else is acting on the object? We know there has to be a centripetal force here, but if we look at the actual forces that are acting on this object, right? We have gravity, but what else is acting on the object? The string, right? So here, we're still looking for the tension force. Here's our tension force. Here's our gravity force. Together, what do the two of these have to end up as? F of c, just like in the problem we just did. So f of c, let's go. F of c is equal to f of t plus f of g. So this looks real similar to the last problem we did, right? What are we going to substitute in here? We're still going to go mv squared over r for f of c. We're still looking for the tension force. But now, when it comes to gravity, we said that gravity was pointing downward. But in the context of our problem, and the circular path that this object is going in. Does it point towards the middle or away from the middle? It points away from the middle. So is it helping us with centripetal force, or is it hurting us with centripetal force? It's hurting us with centripetal force. How are we going to show that here? So at the bottom of the circle, the string has to work harder to apply a greater force. Because not only does it have to make the object go in a circle, it also has to do what? What's gravity trying to do? Pull it downward, right? So not only does the string have to make it go in a circle, it also has to balance out gravity. So if things are pointing towards the middle, like they were in this problem, we go with the plus, right? Helping us centripetal force, we give them positive signs. But in this problem, because the gravity is hurting our centripetal force, we give it the negative sign. So you run that through, and you end up with good there? It might be because of a rounding kind of thing, and that's okay.
Oh, yeah.
Feeling he is okay. All right. Are we okay with that? So in these problems, and we'll work on more of these problems on Friday, we're going to have to incorporate the gravity as now something that may either help or hurt our centripetal force. And we'll pick it up with that on Friday. So, if you haven't done so, get some measurements for the record player so we can work on the coefficient of friction, and then we'll turn that one in for points, and the other one was practice testing. Yes, ma'am.